So for two-dimensional motion, the vector that we most use is velocity. And if we have a velocity vector, then we need to make sure that we break it down to two components, because each are going to be treated separately. So for projectiles, these equations are usually the case. Remember that the labels for cosine and sine depend on the angle. So if I have a vector v, which is what I have here, this is the hypotenuse of our triangle, then if I wanted to solve for the horizontal and vertical components, I would use Vx is equal to V cosine of theta, and Vy is equal to V sine of theta. Remember that your calculator needs to be in degrees for these problems. Also, if a problem asks you for a velocity but it doesn't specify the direction, what they're really asking for is for you to calculate the resultant of the components at that point. So when you are solving for resultant, remember that you need both a magnitude and a direction because we are talking about vectors. So for the resultant, you're going to need to use the Pythagorean theorem, which is this piece right here. Again, we're just combining both of our components of velocity to find one magnitude. And then because you do need that direction, using theta is equal to the inverse tangent, which is this piece down here, of opposite over adjacent. When you're solving for angle, make sure that you understand which angle you're solving for. So sometimes it might be convenient to use this piece of our triangle rather than components already given. So if I were to use this opposite side of our triangle, this is the angle that I want to solve for. So that means Vx becomes my opposite and Vy becomes my adjacent. Again, when I solve for that angle, what that actually tells me, let's say it was 45 degrees, that's not actually the angle of my vector, because I know a 45-degree vector would be pointing up and to the right. Meaning, if my vector is pointing out this way, and I've calculated this angle to be 45 degrees, I know that 270 is from 0 all the way to this point, so that's 270 degrees. Meaning if I add an additional 45, I get an angle of 315, which makes a little bit more sense if you go back and look at our degree circle. Now moving on to projectiles. So a projectile is going to be an object that is being projected through the air by some means and continues to move due to its own inertia. Remember that inertia is just its resistance to changes in motion. So a force is not propelling it through the air. That means you could have launched it, you could have thrown it, but all those forces were only at the beginning, and then from there on, the only force acting on it will be gravity. Because we're working with two dimensions, it's going to be important that you treat the horizontal and vertical components independently. So what that means is when you're solving these problems, it's going to be very helpful for you to make a table of all the X information and all the Y information so that you understand and can visually see that these two things are being treated separately. Last year we talked about two different types of projectiles, horizontal projectiles and ground-to-ground projectiles. So an example of a horizontal projectile would be a ball rolling off a table. The path would look like this. Ground-to-ground projectiles were examples of a kicker kicking a football off the ground, and they had a path like this. Now the third one that we're seeing this year is ground to not ground, and again, what that means is, let's say I can shoot something from the ground at an angle, but then it doesn't come all the way back down. Maybe it lands somewhere a little bit higher than where I shot it from, or vice versa. I shoot a little bit higher than ground, and again, it doesn't land to exactly where I shot it from, but it lands further beyond. So something like this. So these are the three situations we'll see. So for horizontally launched projectiles, our ball rolling off a table, there's going to be two very important things to remember. That horizontal velocity is constant. That's going to be true for all projectiles. Horizontal velocity is constant. The reason that it's constant, and remember that we're treating these separately, is because there is no acceleration in the x direction. Therefore, there is no change in velocity in the x direction. The other thing to remember is that velocity in the y direction at the beginning is equal to 0. So again, if you remember the table and our ball, we can see as it's rolling on the table that the ball is not moving up or down, so its velocity in the y direction is 0 to begin with. As soon as it leaves that table though, then you see that it's going to start to accelerate. So vertical velocity changes due to gravity. So our vectors here show us the velocities at different points. If you can see that the velocity vector in the y direction is going to start increasing. But our velocity in the x direction stays the same the entire time. For two-dimensional projectiles, we're still going to be using our kinematic equations. But now, remember that we need to write them for the x direction and then write them again for the y direction. So if we look at just the first kinematic equation, when we look at the x direction, because we have no acceleration, it simplifies to this version of the equation. And again, we can see that that's going to be true because velocity is constant. When we look at the y direction for a horizontally launched projectile, that our velocity in the y direction is 0 to begin with. So again, it simplifies just to delta y is equal to 1/2 gt squared. We also have ground-to-ground projectiles. These are projectiles that are launched with an angle. So for these, vectors are going to be especially important. Remember that if we are launched with some velocity, that velocity is a resultant of two components. So we need to break it down into its components. Usually we're given an angle. If not, we should be able to calculate it with the other piece of information that we have. So now we have a velocity in the x direction, we have a velocity in the y direction. Remember that because there is no acceleration in the x direction, the velocity is going to be the same all the way through. So if you wanted to draw these velocity vectors, these help us visualize that the velocity is the same in the x direction everywhere. So again, my lines should be identical everywhere. We might need to chop off a little bit there, there, and there. Okay, and for our velocity in the y direction, we do see that as it goes upwards, our velocity starts to decrease. And we're at the very top, our velocity is equal to 0. Remember that our velocity in the y direction is the only thing that's equal to 0. Everything else, our acceleration and our velocity in the x direction, are all some value. Again, as we come down, our velocity is equal and opposite to the other side. Equal and opposite. And again, we start to accelerate as we go downward. So here we have our velocities in the x and y direction initially. Again, remember our new notation, v naught x and v naught y. These are initial velocities in the x and y direction. So to find these components, we need to multiply our initial velocity times the cosine of our angle and the initial velocity times the sine of our angle. These are specifically if we are moving in the positive right direction, which is the type of situation we see in class. Another thing to remember is that if you launch from the ground and end up at the exact same position, you have a displacement in the y direction of 0. A couple of other things. For ground to ground, the time up equals the time down. So sometimes it might be more convenient to solve for the time up and then just multiply that by 2 to find total time. Remember that the velocity at the top is 0 only for the velocity in the y direction. If a problem is asking you to solve for range, it's asking for you to solve for horizontal distance traveled, which is this piece here. And if a problem asks you to solve for max height, you can use velocity is equal to 0 in the y direction at the top to help you solve that. And the last thing, just like in freefall problems, the velocity at some point along the path is equal but opposite to the velocity at the same point before. What that means is if I have a certain velocity here, let's say 25 meters per second, I'm going to be traveling at the exact same speed over here. And so notice how I said speed rather than velocity. The magnitude of my velocity will be the same as it was before, but obviously we're facing in an entirely different direction. So something that might be a little bit easier to look at is our velocity in the y direction. Let's say I have a velocity of 10 meters per second here. Then my velocity at the exact same position on the other side of my path is going to be 10 meters per second as well. But again, because we're opposite in direction, this will be a negative 10 meters per second. Also remember that when you're using the kinematic equations, make sure that you are using the components rather than just the initial velocities. So here we see the kinematic equation for the x direction. Remember, there is no acceleration, so it reduces down to just this piece. And make sure that you use the x component. Again, when you're doing this in the y direction, make sure that you use the y component. Our last situation is ground to not ground. What that means is you're shooting from a certain area and it either lands above or below where you shot, meaning that it does not come back to its starting position. So the time up does not equal the time down. Again, in order for you to have that symmetry, it needs to complete that parabola, but in this case, it doesn't. Here, when I wrote velocity y is not 0, what that means is if it were to hit at a certain position, you might want to try to set that velocity equal to 0 because you think it comes to a stop. Even though that's true, it's not approaching that 0 by itself, like it would under the effect of gravity alone. So here, at this point, you cannot assume that the velocity is equal to 0. One of the other things is our displacement in the y direction, again, is not equal to 0. And actually, that might help you solve problems if you know the height at which it lands. Also, if you have a quadratic equation, such as final position minus initial position is equal to v naught y times t plus 1/2 gt squared, again, this does take the form of a quadratic equation, then you can use your calculator or the quadratic formula to solve for time, t. Now, when you have solved for a time, usually you will get two answers because, again, it's a quadratic formula and it will give you two values for t. One of them will usually be the first time it reaches a certain displacement, and the second will usually be the second time it reaches a certain displacement. It really just depends on what the situation is, so be sure to read your problem carefully. So from here to the end of the video are some example problems. A place kicker kicks a football with a velocity of 20 meters per second at an angle of 53 degrees. How long is the ball in the air? How far away does it land? And how high does it travel? So, anytime that you have a problem like this, again, it's always important to first get components and then make your table separating the different pieces of information from the x and the y. So for my component in the x direction, I got 12 meters per second. I actually got about 12.036300046, but for the purpose of this example, I'm going to go ahead and just shorten it down to 12. For my velocity in the y direction, I got 15.97. Again, for this purpose, I'm just going to shorten it down to 16. So the first part asks us to solve for how long the ball is in the air. So the time up plus the time down. The easiest way to do this would be to solve for the time up and then just multiply it by 2. Again, that's not the only way to solve for it, but I think it's the easiest at this point. So making a chart to separate my information, I have my x and I have my y. So in the x direction, I know my velocity is 12 meters per second. Again, I can just label it as my velocity in the x because I know this will be the initial and the final. For my velocity in the y direction, it is important to label this as an initial because we know that the velocity in the y will change. So this is 16 meters per second. Again, other piece of assumed information is that gravity is negative 9.8 meters per second squared. And we also know that our angle for both pieces was 53 degrees. So I can just label it here at the top. Again, other pieces of information is that the velocity in the y direction at the top is going to be 0 meters per second. And what we're trying to solve for is time. So clearly, we're going to need to use the information in the y direction because it's the one we have the most information for. So, out of our kinematic equations, I think v equals v naught plus gt is going to be the most useful. And again, we're using it in the y direction, so I can go back and add y's. So setting our final velocity in the y direction to be 0. Again, the whole point is to solve for time. So we move negative gt to the other side. And time is equal to negative v naught y over g. When I put all my numbers in, I get a time of 1.63 seconds. So remember that the time that we solve for is not the total time, but only the time it takes to go up to its highest point. So 2 times 1.63 gives us a time of 3.26 seconds. Now that we know the total time, the only side of information that has how far it traveled would be the x information. So this simply becomes velocity is equal to distance over time, where distance is equal to velocity times time. So 12 times 3.26 gives us a total travel distance of 39.12 meters. 39.12 meters. And the last piece, how high does it travel? Again, for this, we're going to probably want to use just the half information of time. So remember that the time up was only 1.63 seconds. So the displacement in the y direction is going to help me figure out how high it traveled if I shorten the time down to just the time that it reached its maximum height. Remember here, you need to make sure that you're using the velocity in the y direction initially to solve for our displacement in the y direction. When we put all of our values in, you should calculate a displacement in the y direction of 13.1. Now for a slightly trickier problem. A baseball is thrown at an angle of 60 above the horizontal, strikes a building 18 meters away at a point 6 meters above the point from which it was thrown. Ignore air resistance. Now it's asking you to find the magnitude of the initial velocity of the baseball, the velocity with which the baseball is thrown. So, for these situations, it's always important to draw a picture. Now, I can start by making a little chart with all the information that I know. Again, x, y. I know my displacement in the y direction is going to be 6 meters. So that's why using vectors is going to be so helpful, because we are talking about displacement. I know that my displacement in the x direction is 18 meters. I know that I've traveled, or I'm being launched with 60 degrees. I also know gravity, so I'm going to go ahead and put that under the y information. Now there are several ways to solve this problem, but I'm going to show you one that's going to probably be the easiest, but not the most intuitive. But beginning to get your mind to this process of thinking is going to help you along the way later. So I know that my velocity, whatever it is going to be distance over time on the x-axis. And actually, it's not just velocity, but v naught cosine of theta is going to give me my displacement over time. If I rearrange this, I now have a equation for time. Again, I don't know all of these pieces, but at least we're getting rid of one unknown. If you can kind of see where this is going, I can go back to my y information and say, well, my displacement in the y direction is going to be v naught sine of theta times time plus 1/2 g t squared. Again, one of the phrases you're going to hear me say all year long, two equations with two unknowns. In this case, I have two equations with time and v naught as my unknowns. I want to substitute. So substituting in for the time equation is going to make our numbers a lot simpler. So I'm going to go ahead and do this on the next slide. I begin by substituting in t. So that becomes delta y is equal to v naught sine theta times time, which is now being replaced by x v naught cosine of theta, and you can already start seeing that a lot of things are going to start canceling out, plus 1/2 g, and again x v naught cosine of theta squared. Now we've gotten rid of time as our unknown variable, and now we just need to clean this up and solve for v naught. So v naughts actually cancel over here, and we know from pre-cal or calculus that sine theta divided by cosine of theta gives me tangent theta. So the left side cleans up pretty nicely. Now the right side's not going to clean up as nicely. I'm going to change this 1/2 to a 0.5, to a 0.5, to kind of get that fraction out of our way. Remember that this is a g. And when you have something that's in a fraction and that's being squared, you need to make sure that you're squaring every single thing. So that becomes divided by v naught squared times cosine squared theta. So again, the goal is to get v naught by itself. So with some algebra, you're going to get delta y minus x tangent theta is equal to 0.5 g x squared over v naught squared cosine squared theta. Again, here I can just move v naught squared to get v naught squared is equal to 0.5 g x squared over delta y minus x tangent theta times cosine squared theta. Okay. And then the last piece, we need to get the square root of this entire mess. Remember to put gravity in as negative 9.8, and you should get a value of 15.9 meters per second. This next part asks us to solve for the velocity as it strikes the building. So remember that when it's asking for velocity, it's not just asking for the x or y, it's asking for the resultant of the two. So now that we know the initial velocity, we can calculate the velocity in the x and y direction at that time. So looking at my information again, I have time is equal to distance divided by velocity. We now know that the velocity is 15.9, or our v naught is 15.9. So that becomes t is equal to 18 divided by 15.9 times the cosine of 60. So the time at which it strikes is 2.26 seconds. 2.26 seconds. And then while we're here, we can solve for our velocity in the x direction, which is velocity x is v naught cosine of theta. V naught is 15.9 cosine of 60. We should get a velocity in the x direction to be 7.95 meters per second. Now we want to solve for the velocity in the y direction as it hits. So we know v naught sine theta is our v naught y plus negative 9.8. And now we know time, so that's 2.26 seconds. So our velocity in the y direction is negative 8.4 meters per second. And that makes sense that our object has a negative velocity in the y direction. So we know that it's falling at that point. So these are our components to our triangle, and what we want to solve for is the resultant. So for that, we simply use Pythagorean theorem. Squared Vy squared gives us 11.6 meters per second. And then the very, very last piece is to find the direction of the velocity of the baseball just before it strikes the building. So we now know that our velocity in the x direction is 7.95. Our velocity in the y direction was negative 8.4. And our resultant, which is the velocity that it actually strikes at, is 11.6 meters per second. Okay. And then, like I said earlier, that our vectors need to have both a magnitude and a direction. So in order to solve for the angle in which it's at, I think this angle is going to be the most helpful. Again, like I mentioned earlier. So you can either redraw your angle or redraw your components, or notice that this angle here is the exact same one as the angle I drew earlier. So to solve for angles, we use the inverse tangent. And here I'm going to use the positive. Unless you really understand the value or the number that using a negative gives you, I really would prefer that you just use positive numbers inside of your tangents and sines and cosines, and then understanding what to do with that number after you've calculated it. So, inverse tangent is opposite over adjacent. Again, I'm using positive numbers here. And you should get a value of 43.4 degrees. Again, I know that's not my final answer because my vector is pointing out in this direction, so 43.4 wouldn't make sense. But I know that that's this angle here. So if I add 270, then I get an angle of 313.4 degrees, which again makes a little bit more sense if you go back and look at our unit degrees, or degree circle, I mean.